All right, today let's look at how to do modal analysis inside LS-Dyna with a comparison to Ansys Mechanical. This is the first of the linear dynamics series that I'm gonna over time release. Basic agenda, we'll look at the overview of the theory of modal analysis. It's really the same thing between Dyna and Mechanical. They're solving exactly the same equations. We're also specifically looking at LS-Dyna to looking at the key control cards and the post-processing method for LS-Dyna inside LS-Prep post. That's really inherently what's different between mechanical and LS-Dyna. And after that, we'll do a very quick demonstration inside to set up an LS-Dyna model. It's really so simple. I might just show the model itself and show the implementation of the control cards. And lastly, we'll do a quick comparison between the dyna results and the mechanical, which shows they're essentially the same, with a slight difference that I haven't figured out why, but I think that's not that important at this point. Most shape are looking exactly the same. Okay, so a quick overview first. So when we're solving problems inside a dynamic system, right, an n-damped equation of motion for a system is basically this right here, which is essentially your inertia term and your stiffness term, right? And if you take the second derivative in response to an external vibration load, you essentially get these two terms, which can be plugged into an equation that look like this. And right here, if you take the determinant of the system, you essentially get a characteristic equation. And if you solve for that, you get an eigenvector and an eigenvalue of the system. And that's essentially what the mode shapes and the natural frequencies are. These are essentially eigenvector are essentially the vector that scales the magnitude of a vector without changing its directions, and eigenvalue is your scaling factor. And both of these two things ends up in a dynamic system to be the mode shape and the natural frequency, which are essentially what you're solving inside a modal analysis, right? And because of that, modal analysis only require you to define the mass and stiffness of the system. There is no external load, and that's one of the things that in my past jobs that I've worked with customers who are very confused about modal analysis is that they think when you see these contour plots that are moving back and forth, they think there is an external load. There is no external load. What we're only defining here is the mass and stiffness of the system. Just like the governing equation indicate, there is no load here, right? Everything is just the mass and stiffness. Everything is equal to zero. And the key use for modal analysis is because it's the basis for all dynamic analysis. So we use that first and foremost as the first step in any dynamic analysis to look at the dynamic response of the structure. Now, in transient analysis, for example, you take 1/20th of your highest mode of interest, and that's going to be essentially your minimum time step or maximum time step you have to take in order to get the response of that mode shape back. What you can also use mode analysis for are to look at the natural frequency of the system versus the frequency of the external load of the external excitations. And if they do match up, or if they're close to match up, you essentially have a resonance problem. And that's a very common thing people look at is to try to avoid the natural frequency of the system. By properly defining its stiffness and its mass, you can properly capture the natural frequency of the system. And then by understanding the external excitations, you can make sure you can to avoid it. You can design the structure such that you avoid the external excitations. What we can also do is check for rigid body modes, and that's a very useful technique when you're solving preparing a model for a very large structure. Any contact problem will show up as a zero frequency rigid body mode, and that's where you can fix your contact. So these are the three very common uses for a modal analysis. Modal analysis can be symmetric, or usually symmetric, but it can also be non-symmetric. If it's a non-symmetric modal analysis, these are the things that you have to take special care to use different command. In Dyna, you have to look at the control implicit solver. There's an LC pack keyword that you have to change. For Ansys Mechanical, what we do is to use the mod option command to invoke the asymmetric modal analysis. I might do a video about this in the future. If I can find a very good example, I can demonstrate the difference between the two. It's not very commonly used. Honestly, I have never really in my personal project used an asymmetric modal analysis, but know that it exists helps. And one of the key things other than mode shape and natural frequency in a modal analysis that you look for is I want to look at the participation factor and the effective mass. These two factors are essentially how much mass is moving in a specific direction, right? So the more mass you have in a specific mode that's moving in that specific direction, the more likely the structure is going to respond that way when it's excited in that direction, at that close to that frequency of interest. So that if that sounds confusing, I'll do a quick demonstration in a bit, right? In a very simple cantilever beam problem. The effective mass is essentially the square of your participation factor. So these two things are pretty commonly used together, but effective mass has the added benefit that adds up to one, right? So if you want to know how much of your system's total mass have you captured in a modal analysis, for a mode superposition analysis, this is where you look at the effective mass. And that's a very useful thing to know for example, if you want to do a mode superposition harmonic or mode superposition, a random vibration or shock response spectrum analysis. I'm going to do all of that inside Dyna. I've always done those linear dynamics problem inside Ansys Mechanical. Well, what I'm planning to do with my YouTube channel is to really expand myself inside the Dyna environment because it is a superior product in almost every other way, right? In almost every way, except it's not easy to use for people. But for me, I want to be able to do the things I can do in mechanical as well as I can in Dyna. So I'm going to master that. So I'll prepare some video about the multi-step analysis in a linear dynamics environment. Okay, so let's look at the key control cards. So how do you do a modal analysis inside Dyna? The way we do that is to use the control implicit eigenvalue keyword. So what I've prepared here, as I can show you, right? So this is a very, if you've been following my video, these are very familiar keyword templates. This is my implicit keyword templates, right? But what I also added here is my control implicit eigenvalue here. This NEIG is the number of mode you extract, right here, right? And this right here, the egg method, this is the method of your mode extraction. Usually you use two for the block Lanzos. And the ROTSCL is your rotational degree of freedom scaling factor. Well, I'm still really figuring this out, but it doesn't seem to have an effect as far as I can tell in the simple problem I created. So I'll probably talk about that in the future a little bit, but I'm leaving that out for now. But with this card right here, right, with this card, you basically can define how many mode to extract and what is the frequency range you want to extract from, right? So center, L flag, alpha end, R flag, RF end. These are the things that you're going to use to define the range of frequency you're capturing. In this case, I'm going to start from 0 and extract for the next 10 modes. So pretty simple to extract them. I don't need anything in the middle of the frequency band, for example, right? And because I'm doing that, this keyword right here, if you insert into a basic structural model with no external load, it's going to extract your mode shapes and your natural frequencies. Okay, and then there are several mode extraction methods inside Dyna. It's very similar to mechanical. If you look at the documentation, they're so similar, right? You have your block Lanzos, you have your fast Lanzos, you have your precondition eigensolver, and then you have this AMSL algorithm that I'm not really familiar with. It's SML SMP only, so I'm probably not going to use that. And then you have the section model. You have the method for section model extractions. So these are the things that are very, very similar to what you would do inside Ansys Mechanical. And what a eigenvalue problem also require inside Dyna is that you do have to include the standard implicit control cards. Without them, the job would basically not behave pretty weirdly. You can do like because you essentially default to explicit, and that's not really what you want for a modal analysis. You want to solve that implicitly, and then you have to include these implicit control card, which is why I have a very clean implicit template control card template that I'm adding the eigenvalue control card to, and this together I can just copy paste into my problem, and that will allows me to basically solve the problem, so solve the modal analysis. And lastly, once the problem is finished, what you will get is a D3 egg file. This is your mode shape file. You just import it as like a D3 plot, and then you have the egg out file, which is where you get your participation factor and your modal mass from this text file. And this text file will look something like, say for example, this, right? This is your participation factor, effective mass, and this is your scaling factor. This is essentially your eigenvalue, which is just eigenvector scaling factor, and that's where you get to see the information that you otherwise see inside the Ansys Mechanical window. Okay, so let's look at a quick simple problem. I'm not gonna do this. This is so simple. It's almost stupid. I don't really wanna take my time to do stupid stuff, right? I want to keep the video below 15 minutes. It's actually better for everybody, right? So if you look at this, I have a fixed support line in, then I'm extracting 10 modes, and you can sort of see this is the first mode, second mode, right? Third mode. I'm just gonna play it real quick, right? Fourth mode, and you will see these modes are exactly the same as you will see in Dyna, which means that they're solving the same equations, right? And even though this is a very simple problem, there when you go to the very complex problem, it's exactly the same situation. You're solving the same equations, just with a different overall system that you're solving with. So you're looking at a different system, stiffness matrix, mass matrix, but you're solving the same equations, so you're gonna get the same response back. Okay, now inside LS-Dyna, it's basically exactly the same model, right? I have my everything else the same. I have my fixed support on one end. I'm making sure my element formulation is 2 for a brick element, like you see here. It's a linear brick element that I'm using. In mechanical, I think you actually default to a quadratic element with like a compatible modes or something like that, which might be the reason I have a slight difference in my result, right? Which actually might be the now that I think about it, that might be the reason I'm getting zero rotational degree of freedom. But I'll get to that in a bit, okay? But in this case, I have these right here. Now, if in the mechanical side, all I'm doing here is I'm literally just copy pasting this template, bam, and then bam, copying here. Okay, once I copy here, you see this card right here. That's going to basically solve it. And once you solve it, what you see here is you see essentially you just go to File, Import, and you just import the egg D3 egg V file in here. And what you can sort of see here is that you have different mode shapes, right? 1, 2, 3, 4, 5, 6. And they're exactly the same mode. So for example, mode 8 over here should be the same thing as a mode 8 over here, right? So it's an extension mode. Okay, and then even the scaling factor might be different, but that's just your eigenvalue of your eigenvalue problems. It's just a scaling factor in that regard. Okay, so you can see you get basically the same results. So if you want to do a quick comparisons, right? These are my mole natural frequencies. This is the natural frequency for Dyna, almost one to one the same thing. There are slight differences, which I actually think now that I think about it, it might be because I'm using different element formulation between different programs, different code. That might be the reason. Over here, I'm using an 8-noded brick with a Alform 2. Over here, I'm using a 20-noded brick with like enhanced string formulations, which I believe is a workbench default. So that's something I can investigate and make sure I understand. And that also might be the reason. You see, I have zero rotational degree of freedom over here, even though I have more inside the mechanical side. This is the only discrepancy that I haven't been able to resolve. So something I'll follow up on myself in the future as well. But otherwise, you get very similar responses if you look at it, especially where your participant factor is high, around mode 8, right? 0.1089, 0.1089, 0.4789, negative 2, 0. So you get a very similar 9.47 into negative 2, 9.47 into negative 2. You get very similar responses, especially around places where you have a higher participation factor. Same thing on the effective mass side. So I won't show that to you. It's basically the same thing. So essentially, between mechanical and LS-Dyna, we're getting exactly the same results because we're using the same mode extraction methods. We're solving the same problem. The only difference, then I think about it, it might be because I'm using different element formulations, element order, element formulations. That might be the reason I'm getting a slightly different result, which is reasonable if that's the case because your stiffness matrix is gonna look a little bit different. But the basic problem becomes the same. And this is gonna be how you do a modal analysis in LS-Dyna. In the future, I'm gonna do a next video. I'm gonna do a pre-stress modal analysis next week, and then the following week I'll do a random vibration. Then the following week I'll do a response spectrum. Then the following week I'm gonna do a harmonic analysis. For the next 3 to 4 weeks, I'm going to cover the entire linear dynamics band, including a few side videos about how to do, say, for example, fast Fourier transforms. I want to complete that linear dynamics package inside my YouTube channel especially with a very clear comparison to Ansys Mechanical to prove that you have the very similar workflow and you have almost almost exactly the same results at the end. Okay, thank you very much.